We're in class 11 for ME470, dealing with roller bearings, rolling element bearings. And we're going to start out with an example. So this is a longish example. Want to make sure that we can still do a 3D shaft problem. I know, you love the 3D shaft problems. Well, here's another opportunity to do one. So, and there's a lot of 3D shaft problems in Shigley. So here it is. This is problem 1132 that I said it was modified. The figure shown is a geared counter shaft with an overhanging pinion at C. We want to select an angular contact bearing from the available table. And we know from this right here that the force on gear A is 600 pounds and the shaft is to run at a speed of 420 RPM. Specify the bearings required based on the bearing carrying the most load. Okay, so that means that there's two bearings. One of them is going to carry a lot more load than the other, but we're going to size them for both the same thing. So we have to double check each of them. And we want to use an application factor of 1.2, and we have a desired life of 40,000 hours and a combined reliability goal of 95%, assuming a distribution data from manufacturer 2. Okay, so there's a whole lot of information right there. Let's check this out in the book right here. Let's see what problem this is. This was problem 1132, and they probably just told us that we were gonna. They probably just in here somewhere it says. We'll look at the old one, right? So it looks like it right here. It's going to be problem 1134 now. Let's say, or 35 or 34. Interesting here. Okay, so the solution from the stacks problem. So they already did it for us, and they used 600 pounds and 420 RPM. See, I normally would have given you this probably with the power, and then you could have figured out what these forces are going to be. You know how to do that now, right? And wow, that's the thing zooming back and forth. It doesn't like coming in. So anyway, this is the problem that we're working through. So I didn't invent the problem. Maybe I should have, because I definitely would have given you the power, and instead of just giving you the force on the thing. But they did tell us that the force right here was equal to 600 pounds, and because of that right there, right, we could find out what the power is going to be. We could take 600 times the cosine of 20, boom, and the diameter is 24 inches, so we could say that we had multiplied by 12, so that's the torque in inch pounds. I'm trying to remember, do we use foot pounds? And I really need to memorize these things one of these days, but I know I can't remember with that 63,000 if that's inch pounds or foot pounds. That is inch pounds, right? So if you take that pounds right there, inch pounds, and you multiply by 420 and you divide by 63,025, which is from equation 342, you get that this thing is doing 45.1 horsepower. So I think that's important to kind of know when trying to think about the size of stuff. Think about what size engine or thing might have 45 horsepower. Well, a very small car has right around 100 horsepower, right? A kid's dirt bike, not a grown man's dirt bike might have 50 horsepower, right? Or something along those lines. But anyway, a lawnmower only has a riding lawnmower probably has less than 20 horsepower. So you can get kind of an idea of various things about how big this thing might be. So we want to figure out what the other force is. They only gave us FA, so I think the best way to do it is to do a free body diagram right here where we have the 600 and we have our 20 degrees. So this is the big eye looking this way right here. And this guy is coming off right down there, and that's apparently 20 degrees as well. So that's going to be our FC. So, oh, and by the way, let's see, I decided that FA. Okay, now this is, by the way, I'm going to make sure that I get this right. This is the Y, and this is the Z direction. So the FAZ is going to be our 600 times the sine of 20, which is 205.2 pounds. And then the FAY is 600 times the cosine 20. So we get 563.8 pounds. So if we do the summation of the moments about the x-axis right here, we're going to see that we're going to go negative this one right here, right? 5, 6, 3, and I can't read my own writing, that's an 8. Times our 12 right here. And then this one right here, remember that's 20 degrees, so that's going to be plus FCXZ. It's in the Z direction, sorry. Z times the cosine, well, no, not cosine, because I'm actually getting the value, right? So I'm not going to get bothered. It's just easier for me to stick with the x, the z, and the y instead of getting the magnitude here. So we'll just get that component, and this is apparently 5 radius right there. So we get the FCZ is equal to 1,353 pounds. So we can get the CY is going to be that 1,353 times the tangent of our 20 degrees, or 492.5 pounds. Now we do some of the your very favorite things in the whole world is to do the statics. We don't need a shear moment diagram, but we really should do. We do need to have this in 2 planes. So I'm going to try to use less space here. I'm going to have this is my X, and this is my Y right here. And now this is my Z right here, and this is my X. And I'll sketch this thing out. We'll draw this in. I'm going to make similar sketches. And I'll make the shaft in there. Make it look correct, or thereabouts. And it'll be a good practice here to do the. If you did your shaft project in Excel last semester, you could and you set it up the right way, you could probably have harvested this. But although this is kind of a weird one in that this has a cantilevered section onto the thing, right? So I'm going to draw the bearing as like a little X in there, so you can see that there's a bearing here, and that. So this is going to be like O, and this is A, and this is B, and this is C over here. Same thing, O, A, B, C. And so looking at the X and the Y right here, this thing, you can see it's going to go upwards right here. And that right there is going to be our F, A, Y. So it's going to be the larger of the two. And then looking at this one right here, this is going to be this downwards component. So it's not, and I'm even drawing it onto the top of the thing right there. And this is a skill that you must have in my class. All right, so we have to learn statics. All right, so the reactions that are taking place here, this is actually going to be, this could be a teeter-totter. We're not 100% sure. It depends on what the magnitudes and these distances are. Remember that this is 20, this is 16, and that's 10 right there. Right? Same thing here. This is 20, 16, and 10. I might put my B too close into there. So when it comes to which directions, it seems to me that this guy is going to be, I drew them both on mine as being upwards, but I know that they got to be downwards. I'm almost certain this one has to be down, right there. I'll call this the ROY. That's my Roy. And this one right here, though, is kind of a toss-up, whether he's going to be upwards or downwards. I'm looking at my results right here, and it ends up being upwards right here. It's because of like a teeter-totter effect that's going down. So I knew this one was down, and I know this one was up. If I'm not sure, maybe I assume that they're both positive, and so that I can find what they're going to be right in there. And let me finish up the diagrams, and then I'll do the statics on both of them. All right, so this one right here, we're looking down upon it, right? So we're looking down here with our creepy eye onto the thing. Actually, our eyelash is going to go that way. So when it comes to this force right here, it's going to be the radial version of the thing, and it's going to have our FAZ. And then this one right here, we're going to be seeing this larger component of it, and I even put like the tip of the arrow right here on the top of the thing to try to kind of give myself the orientation of the piece right there. Okay, so I'm going to start writing the thing out over here. I would like to keep it underneath this as much, but I think I'll be cramming it in there too much. So I'm going to write the sum of the moments. I'll do it about O. And so I'm going to take my FAY as counterclockwise. So that's my 563.8 times 20. And then this guy right here, I assumed he was counterclockwise, so let's hope I got that right. And then this guy is going clockwise, and he was 492.5. Oops. I forgot my moment arm. Silly me. So that's going to be 36. And then minus, now we put it on here, 492.5. And that's going to be, so 36 is going to be 46. 46 equals 0. And I get my RBY is, I'm going to trust my numbers, 316.1 pounds. And it was positive, so I picked correctly. And now if I do the sum of the forces in the y direction, and I picked negative Roy, so I drew it negative, so I'm going to keep it that way. And it's going to be going up my 563.8. It's going to be going up my 316.1, and then it's going to be going down my 492.5. I didn't write it out all the way. So my Roy, I end up getting a positive value, which I happen to know means that I chose correctly. as being down. Right, so all of that was associated with that left diagram. I'll do the same thing over here and do it for this diagram right here. So I really should maybe use up more space, but I'm going to try to get it all on one piece of paper because my original one is all very messy. I want to kind of replace it. I don't like how it looks. I don't like it with the colors on there. I don't know why I was using color pens back then. I think I was bored. I was trying to make it look interesting. I don't know what I was doing. But anyway, by the way, this is the sum of the moments about the z-axis, and this is moments about the y-axis. So we could make a distinction there, right? Because the y-axis is coming up right this way right here. So we're doing the moments that way. So let's see. We're going to take the FAZ, and that's counterclockwise, so it's positive. So that's 205.2 and multiply by 20. And okay, and I didn't choose the directions on here, so I'm going to choose them. Did I choose them wrong before? I think I did choose them wrong. This one right here, I think you can almost be certain that one. I think so. So this is going to be the ROS. I'm going to call it ROS because it's the at RO in the Z direction. This one, let's see, BZ. Yeah, I chose them going to be in that direction. And once again, you don't know for sure. This the ribs. You don't know for sure sometimes which direction these are going to go when you have like this off when these two are in the opposite directions. But you can kind of guess a lot of times just by the magnitudes. But you want to be cautious not to choose the wrong direction and get a negative and then think that I don't know. Just a lot of times, if you don't know, choose the positive direction. You'll be and then you'll know whether you got it right or wrong. All right, so that's coming this way. We're going to go positive with this one too. So this is the unknown ribs, and he2 is 36, so it's kind of similar to this what we did over here. And then now we're going to have minus and this FCZ. So this is going to be a very large number compared to the other ones right here because he's a small gear, so he has a large force onto him. And his thing is 46 right here. So our RBZ as part of this is going to be 1,615 pounds going that way. And then summation of forces in the Z direction. And let's keep it consistent with how we've drawn the axis. So downwards is going to be positive in this case. So we have ROZ as we've drawn it, and it's going to be minus FAZ, which was the 205.2, and then we also have what we just found, 1615, and then we're going to have, that should have been negative, my bad, because we are going in the negative direction there. And then we're going in the positive direction with our big load of 1,353, and that's going to be equal to 0. And we find that our ROS right here is now going to be 467, and we should have had some change, but I guess I didn't round off on there. So anyway, that goes down. We end up with a positive number, so we know that we got our assumption was correct right here. So now what we want to do is find out what the magnitudes of each of these forces is going to be. It just fell. Okay. So let's figure out what RO is going to be the square root of 387.4 squared plus 467 squared, and I get that's going to be 606.9 pounds. Whereas we have RB is the square root of 316.1 squared and 11615 squared, I should say. And so 1,646 pounds. So this one is the larger of the two. And if we go back and read what we were supposed to do as part of this thing, we want to specify the bearings required based on the bearing carrying the most load. B carries more than twice what O does right there, right? So let's take a reflection onto that right here. This thing is cantilevered off from the end off of the thing, so it's got a lot more load being handled right there at that spot. Okay, so what do we do with it? Well, let's turn it into kilonewtons. So in order to find the kilonewtons onto the thing, we might want to look up for the conversion factors. And I don't think I do that very often. And Shigley doesn't have a really long list of conversion factors, which is kind of a, it's kind of a, I don't know, I guess nowadays people just use it, look it up on the internet. But it used to be a pretty useful thing to have, like really good a bunch of conversion factors for all the different units that you could possibly have. But now I guess we're over that now. So let's see what we're going to use. We want to turn pounds force into newtons, and so you multiply that by 4.45 to get into newtons, right? So 4.45 times the pounds. But we want kilonewtons, so we take 1,646 times our 4.4, and I just forgot it. I think it's 4.448, by the way, and then divide by 1,000. And if you're to believe my old number, I got 7.321 kilonewtons right here. So now we want to use that in conjunction for what we learned about bearings, right? And some things, preliminary things we want to do. This is a little confusing because I'm using R here, but this is the total. It needs to be 0.95. Total reliability needs to be 0.95, which means that the reliability of O and the reliability of B need to be there. So the individual reliability needs to be the square root of 0.95, right? Which ends up being 0.9747. So 97.5% reliability is required in order to get a total combined reliability here. And I said that I was going to switch over to the new, not the new, but the other of the two equations, basic equations that we're going to use here in Chapter 11. So I will follow through with my claim that I'm going to do that. And so I am going to use this equation right here now. And we need to use the Weibull parameters from from table 6. And they are right here. All right, so we find the Weibull parameters right here for the reliability, and this is manufacturer 2, and we're basing it on 1 million cycles, and here are these Weibull parameters. And so let me write this out onto here. Let's see if I can figure out a place to put the book on my lap. And so I'm writing out C10 is equal to AF times FD, and we just found FD right here. That's our desired, times XD, which I didn't calculate anywhere around here. I should have done it over to the side. I think I did it actually up here, so I might go do that again. I'll calculate the XD. It's just kind of nice to get it over to the side. And here are my Weibull things. Minus XO right here. And then it's going to be the natural log of 1 over RD. So that's our RD. RD desired is right there. And that right there, after we do the natural log, we raise it to the 1 over b. And that's that whole thing raised to the 1 over a. Now, let me get my xd out of the way over here. So my xd is going to be my Laverne times the RPM times 60 divided by my, I think I wrote it wrong. I think it should be LR, so that's the rated right here. So that ends up being 40,000 times 420 times 60 and divided by 1E6, and we're left with 1,008. Right, so we have an XD of 1,008. So let me plug all these things into here. Told us application factor. We just found this. We had this right here. Over to this. Our y-bowl factors are 0.02 plus, and this is the 4.459, I think, minus 0.02. Here's where I get a little bit of difference, 1 over 0.9747. And I ran out of room, of course. 1 over, I got to see my own words, 1.483, 1.483, all raised to the 1 over 3. I should just use more paper. Should just use more paper. I tell people that all the time, but not taking my own advice. Most people don't. 1.483. Okay, so I think I'm going to work backwards in this. I use a Hewlett-Packard calculator here. So reverse Polish notation, you start to learn to start like a different spot right here. So 0.9. Actually, I'll take 0.95. I'll take square root of that. So now I have the actual number. And I'll take the inverse, and then I take the natural log of the thing, and then I take the 1.483, and I take the inverse of it, and then I raise it to the thing, and then I take 4.459, and I subtract out the 0.02 from it, and then I multiply by those two things by each other, and then I add in 0.02 plus, and now I have the denominator onto the thing, and now I have a 1,008. I divide and then flip it over. So now, okay. So now this whole thing inside here is 2,549. I'm going to take it to the 1/3. So let's see, raise it there, and then I raise it up right there. So this whole thing is 13.66 as a multiplier times that thing. So wait a minute, I have 7.321 times, right? So already I'm at 100, almost exactly 100, and then I multiply by 1.2. So I have the C10 of this is 120 kilonewtons, which is pretty big for our this table that we have right in here. So we come into this 11.2 here, and what they say? They said to have an angular contact bearing, right? An angular contact bearing. But if you see the angular contact bearing, whoopee, all the way down here, has a bore of 95. In order to get it to that large, we get 95 millimeters. 95 millimeters, that's a big bearing right there. You know how big 95 millimeters is? Divided by 25.4. 95 divided by 25.4. That is 3 3/4 inch shaft. 3 3/4 inch shaft onto the thing. This big of a shaft, right? That's the diameter of the shaft. Now compare that to the size of this right here. It's 10 inches, right? So this thing's that big, and so that shaft is coming in to be here, right? So here's the 10-inch, and there's that. That's a pretty big. That's a pretty big bore of a bearing, right? And imagine we had to put the step in there. So I'm wondering if maybe this design of this length isn't too far over cantilevered with that 10 right there, right? These design choices that we might have to make. So anyway, if we were going to specify this right here and go with what they said to do, it's going to be an 0295 angular contact bearing. Is going to be the specification that we would use. It's quite big. Now we might want to try to use a roller bearing instead, because you'll see that their capacity, they have quite a bit larger capacity, especially this 03. We have ones that could be smaller. So like if we head right to there, we could have a 60 millimeter. Maybe that's the way to go. It doesn't. There's a certain amount of compromise that we have to make. It doesn't handle that angular displacement too much, so maybe that's a consideration as part of it. And it doesn't handle any amount of thrust, which is what we're going to do with the rest of the class today. Is going to be talking about how to merge thrust with our how to account for thrust in a bearing, right? So that we can have both combination thrust and radial in the same bearing. Sometimes you'll have separate bearings for them, but not always. So this was 32 minutes. It's a long example. I'm going to take a look and show you that this was the solution. Should I? Let's take a look. Let's take a look at the solution manual. Okay, so I think I see there was actually some difference between what I did and what is in the solution manual. First off, you'll see that they have the combined reliability right here. They use the 0.975. They got the same thing here for the XD. We could also see that we had the 607, yep, and the 1646, sure, when it came to the total amount of bearing loaded each. But here what they decided to do, they decided to use an angular contact bearing on the smaller at point B, right? Instead of using the same bearing at both places. And I don't know if I said to do. I think I changed it right here. Yeah. It said select an angular contact bearing for bearing O and an O2 series cylindrical roller bearing for at B, right? So what's going to be different here is obviously they found, and they went ahead and they did the conversion after right here. So they used the 607, and they were able to find an angular contact bearing at O right here. So that's fine. And then at B here, they what they did is, you notice there's a difference. They used a different exponent. So they used a cylindrical bearing, so 3/10 right here. And so they got a slightly different number than us. Like I got 120, but by using the 3/10, they were able to get, then it makes it just a slightly smaller, but then they're able to find that they can either use an 0275 millimeter, so they had 92.7. So they're going back into the table over here, and so with the 92.7, they're able to either come in here for the C10 and 92.7. Yeah, they're able to get the 75 millimeter in here, or they're able to get the this right here and use the 55 in the 03 series, and that's going to be depending on the geometry of the housing of whether the 03 versus the 02 is going to fit, and also considering some of the other shaft diameters. So I figured it's worth just taking a look and then comparing to what's in the book.